Hello everyone and welcome back to part 2 of the Unit 4-4 notes. In this video we're going to pick up where we left off on page 4 and we're going to find the inverse Laplace transform of this capital Y of S here. You'll see that this looks much more like something you found in Calc 2 that you had to find the partial fraction decomposition of. So this part should feel somewhat familiar. I'm going to remind you, although we're going to approach this problem from a different direction to find the coefficients, you can do it like the Calc 2 version where you expand everything and then equate coefficients with the numerator. But we're going to do it in the new fashion. So let's first come up with what we think the partial fraction decomposition should be. So you'll notice we have a repeated linear factor, s minus 1 quantity squared. Since that's a linear factor just repeated, you just put a constant above it. Start with a constant a, and then next you count downwards until you get to that factor to the first power, so we only had to do one extra step here. We put a b above that, and then we're going to get a c over the s plus 3, right? And now if I recombine this into one single fraction, let's see what I get. Well, my common denominator is going to be s minus 1 squared times s plus 3. I want to caution you, you do not multiply all three of these. You'll notice this s minus 1 is not contributing anything that the s minus 1 squared already does not contribute, right? Okay, so just to make that clear. That was a common mistake in Calc 2, and I just want to make sure that we get out in front of it here now that we're in differential equations. So let's go back and adjust now, okay? So let's see, this a already has the s minus 1 squared, so it looks like it just needs the s plus 3, right? The b, it has one of the s minus 1s, so it needs another one, and it also needs the s plus 3. Now the c, it already has the s plus 3, so that means that it needs the s minus 1 squared. Okay. And so what that tells us, equate numerators now, right? That tells us that s squared plus 9s plus 2 has to equal a times s plus 3 plus b times s minus 1 s plus 3 plus c times s minus 1 quantity squared. Okay, so what we're going to do now is pick s values to help us find what a, b, and c are. So the first one that you may consider choosing is s equals 1. Notice it knocks out these two terms here, right? The one with the b and the c. And so if we plug in s equals 1 on the left-hand side, we get 1 plus 9 plus 2 is 12 equals, plugging in s equals 1 here, you just get a times 4, and then everything else has this factor of s minus 1, which means when you plug in 1, it goes to 0. And so this says that a equals 3. Okay. The next one I would plug in is minus 3. Hopefully you're seeing that as well, because it knocks out these two terms here, the one with the a and the b, and then you'll just be left with something containing only c, which you can solve for. So plug in minus 3. We get minus 3 squared plus 9 times minus 3 plus 2 equals c times minus 4 squared. So the left-hand side is 9 minus 27 is minus 18 plus 2 is minus 16, and here I get 16c. And so I see here that c equals minus 1. Now, since I know what a and c are, and I don't know what b is, and I've exhausted all of the s values that like cancel off terms, notice minus 3 is used up, 1 is used up. That means we usually try something else. 0 is usually a good choice just because it's easier to compute some of the values. So if I plug in 0 to the left-hand side, I just get 2. If I plug in 0 to the right-hand side, I get a, which is 3 times 3, plus b, and now I get minus 1 times 3, plus c, which is minus 1 times minus 1 squared. And so let's see what that tells me. I get 2 equals 9 minus 3b minus 1, right? And so solve for b, you get b equals 2. Okay, so here's our partial fraction decomposition then. Capital Y of s equals a, which is 3 over s minus 1 squared, plus b, which is 2 over s minus 1, plus c, which is negative 1 over s plus 3. And so that means that little y of t is the Laplace inverse. And now you can just split up at these plus signs here, right? So it's the Laplace inverse of 3 over s minus 1 quantity squared plus Laplace inverse 2 over s minus 1. And that minus can factor out, so it's minus Laplace inverse 1 over s plus 3. And 2 of these we know how to solve. Notice this Laplace inverse here would be 2e to the t. This one would be minus e to the minus 3t. But here, this first one, we actually don't know how to solve yet. But here is the expression for it, so add this to your table. In the right column, you'll get c divided by s minus alpha quantity squared. And in the left column, you get ct e to the alpha t. All right, so now little y of t is therefore, well, what's our c value? 3, and alpha is 1, so you get 3t e to the 1 times t plus 2e to the t minus e to the minus 3t. All right, moving on to the next page. So looking here, we see that given that the Laplace inverse of this expression here, like we found on 2 pages ago at the end of the last video, remember I said add these to your table? Well, here they are again. Can we explain why it's important to write the numerator in this form as opposed to this form? This is an important observation to make. It's important to write the numerator in this form here because when, like we saw, when you split it up, each of these is their respective either e to the alpha t cos identity or e to the alpha t sine identity, right? But this idea extends even further than that. It extends to this new expression we have here. So when we're dealing with repeated linear factors on the bottom. So let's first find this one, and then you'll notice I added a couple more exercises just for some extra practice. But let's find the Laplace inverse of this one right here. Well, you'll notice, what do I need the numerator to look like? This looks just like a constant divided by s minus alpha is 1 and beta is 2, right? I think we've seen this denominator before. So that means my numerator, it needs to have a factor of 2 in it because that's my beta value. So as we've seen in a previous video, you're like, okay, I need a 2 up there, but it wasn't there before, so I need to multiply by 1/2, right? And now you'll notice this 3/2 can factor out. And the rest of it is, I think, the sine identity. If you think of 4 as 2 squared, then it's this identity right here, right? And so this should be 3/2 e to the alpha, which is 1 times t times sine of beta t, and beta is 2. Right? Okay, so now let's come to this one. This one is possibly even more interesting. Let's see here. Now we have an s in the numerator, so we probably need to get it to look like this, right? If we're going to apply the inverse Laplace transform to it. So what we're going to do, now watch very carefully. I need not just an s, but a quantity s minus 1, right? So just like in the previous exercise, do that and then account accordingly. So if I'm throwing in an s minus 1 here, I initially had a numerator of minus 6s. But now what is my numerator? My numerator is minus 6s plus 6, right? So I need to subtract off that 6. Okay. Oh, well now look, this first term on the top here divided by the denominator will be a cosine identity in the Laplace transform. And this one here will be a sine identity. Well, let's see if we can identify which one. Now 6 is actually 3 times 2, right? And the reason I'm thinking of it like that, look at the last example. 2 is the beta value. And now the inverse Laplace is just the inverse Laplace of each. This one is minus 6 e to the alpha, which is 1 times t, cos beta, which is 2 times t, minus, and now the 2 gets absorbed with the sine identity right here, right? So the fact that beta is 2 gets absorbed, but the 3 does not. So this is minus 3 times e to the alpha, which is 1 times t sine beta t. Okay, and now this one we're going to do something similar, right? So notice we have a repeated linear factor on the bottom. So if you encounter something like this, one thing you could do is the following. Well, just kind of bear with me on this one. So I'm going to put s minus 2 here, but let's see, what do I need to account for? My numerator has to be 5s minus 1. Right here it's 5s minus 10. So I think I need to add 9 back on, right? Well, this is the Laplace inverse of 5s minus 2 over s minus 2 quantity squared plus 9 over s minus 2 squared. Oh, notice here in this fraction, the s minus 2's cancel. And so I get Laplace inverse, and now I'm going to split up at this plus sign here. Get Laplace inverse of 5 over s minus 2 to the first, right? Plus Laplace inverse of 9 over s minus 2 squared. And now this one, the second Laplace inverse, is this identity right up here, which you just added to your table. Notice alpha is 2, c is 9. And this one here, we already know. We've done this 1,000,000 times. This is a normal exponential identity. And so there you go. All right. So I'm not going to spend too much time on number 6. But what I will say is describe these methods in a way that makes sense to you. You can stick with the Calc 2 method if you like. But with irreducible quadratics, I really hope you'll do it the way that I illustrated in the last video. And for the homework, I think this last page where I gave a couple extra examples will help with some of these. And you'll notice once you know how to do Laplace inverses, you know how to solve differential equations with the Laplace transform. We'll do an example or two in when we get into Unit 4-5. So if you want, just hold off on doing these until then, or go ahead and give them a shot.